think we are okay for sound, and we are recording. All right, we're in for an interesting class tonight as I introduce hypothesis testing. Going to be a fairly conceptual class tonight, although I do have a couple of examples here that PowerPoint will allow me to start the slideshow. Yeah. There we go. Okay, the only problem I'm having is that my keyboard isn't working. There we go. Huh. Yeah, it was just working, but it's not working now. I can advance the slides with the mouse, though, so I guess I'm okay. Okay, so we covered confidence intervals last week, and I'm going to start this week with we'll review confidence intervals, and I'm going to introduce hypothesis testing, starting with the relationship between confidence intervals and hypothesis testing. We're going to cover both hypothesis testing about a population mean and a population proportion. We're going to talk about these concepts of the null and alternative hypotheses with some examples of calculating test statistics and p-values using the the standard normal distribution and the t-distribution for one sample. And I will introduce type 1 and type 2 error to you and just start on power, which we'll get into more in the next class. So to review confidence intervals, remember that these provide an estimate of your population mean along with a margin of error, which gives you the value above and below your point estimate within which you have a certain pre-specified degree of confidence. And that associated level of confidence can be interpreted as the probability that the interval contains the true population mean, with that that interval being specified by the margin of error plus or minus, above and below the point estimate. And another way to think of it is that this estimated confidence interval provides a range of population means that are consistent with your sample. So as you perform repeated sampling, the mean of your sample will vary with random sampling variation, and this confidence interval contains that uncertainty in the sample mean due to the sampling error, as we understand from the sampling distribution, and provides an interval where your sampling error is consistent with a range of population means. So to construct a confidence interval from a sample, you have to calculate this margin of error. And that is the amount above and below the population mean that your 95% confidence interval or any other confidence interval lies. So if we're talking about 95% confidence intervals and our sampling distribution is normal, then the margin of error is 1.96 standard errors. The margin of error is 1.96 standard errors if it's a 95% confidence interval and if our sampling distribution is normal. Whereas if the sampling distribution is t-distributed, because we're estimating the standard deviation from the mean, then that margin of error is estimated using the critical value from the t-distribution. So this t alpha over 2 means that for a 95% confidence interval, alpha is 0.05. That gets to this equivalence with hypothesis testing that I'll be talking about you with. But you look up this critical value of t for the specified level of alpha and the degrees of freedom of your t-distribution, which is just your number of observations in the sample minus 1, and multiply that by the standard deviation estimated from the sample divided by the square root of the sample size. Now, this is something where these tables of t-distributions are pretty convenient. You can also use something like the t-distribution function in Excel, but if all you need to do is look up the critical value, the table's actually pretty handy. So, for example, for alpha equals 0.05, then alpha over 2 is 0.025, which would be, so one tail would be 0.025, two tails would be 0.05. That would be this column. If we had 22 degrees of freedom, we would follow down to here and find the critical value is 2.07. And I did another little look up here just to show. So for now, this is a 50% confidence interval. We don't even have that in the table, but I calculated it. The ratio of those two is 3, which just gets up one of the key things that I was trying to drive home last time, that in order to have greater confidence, like a 95% confidence interval instead of a 50% confidence interval, your interval has to be wider. And if you're going with 22 degrees of freedom in a t-distribution from a 50% confidence interval to a 95% confidence interval, that ratio is 3. The 95% confidence interval is 3 times bigger. So, key points. The sampling distribution is where we calculate these confidence intervals from, the standard error of the sampling distribution, and it is the area that contains 95% of the probability in this sampling distribution centered around the sample mean. You should, by now, be comfortable with the interpretation of confidence intervals as an interval that you can be 95% confident contains the true population mean. It's not about individuals, it's about the population mean. Or alternatively, with repeated sampling, it is the proportion of confidence intervals that would contain that true population mean. And you should be comfortable with estimating confidence intervals from the data using either t-distribution, a z-distribution, or for proportions, where you just had a different formula for the standard error with the square root of p times 1 minus p in it. These are all good things to keep in mind when you're studying for the next exam. So why hypothesis testing? We have confidence intervals. Hypothesis testing is useful when you just want to answer yes-no statement. So that yes-no statement could be about, say, whether a population mean has a hypothesized value. That would be a so-called one-sample hypothesis test. Or say whether an intervention causes a measurable effect relative to a control group. That would be an example of a two-sample hypothesis test. A couple examples. Do hypertensive smoking men have the same mean cholesterol level as the general population? So that's a one-sample test. We have one sample of hypertensive smoking men, and we have some mean cholesterol level that is known for the general population. Or does intermittent screening and treatment for malaria improve health and education of school children in a certain area? So this would be something like this intervention and control group. So you would have to have here both an intervention group with the screening and treatment and a control group without that, where you compare some measures of health and education of school children in some area. We're going to go into this example in some more detail. I've attached this manuscript to tonight's lecture notes just as an example of hypothesis testing where the methods are a fair bit beyond this class. This is a cluster randomized trial, something that you're not going to learn about for another year or so. But it's a nice example because it contains a lot of the things that you've learned and that you should still be able to interpret, even though you don't know all of the methods yet that were used to get to these. But it contains results that should be recognizable by now. Just a sec. Whoops. Giving away my joke here a little early. Okay, so I'm just going to quickly talk about this abstract here. The title of the paper is Impact of Intermittent Screening and Treatment for Malaria Among School Children in Kenya, a Cluster Randomized Trial. And this was a study in Kenya where there's a high prevalence of malaria, and the researchers introduced this intermittent screening and treatment for a number of schools. So it's a so-called cluster randomized trial because the randomization had to occur both at the level of schools and at the level of children. Because if there's, how many, does it say right here how many schools they tested? I forget how many schools they looked at, but if you have, what's that? 101. 101 schools. So you can't very well implement intermittent screening and treatment for one individual in a school and not another one, and do this across all 101 schools. But what is practical to do is to take, and part of that is because the screening process is implemented for a school. It's not implemented for an individual. So this is getting a little bit of an aside here, but they assign schools to be treatment or control groups, not individuals. And then they sample individuals from those schools to observe the outcome. But the unit of randomization as far as the treatment goes is the school. So a whole bunch of students are either put in the control group or put into the treatment group. So you don't know how to analyze that yet, but you do know how to interpret a number of the results. So the randomization was performed, and then they were followed for up to 24 months. And there were a number of outcomes here relating to anemia and sustained attention. So a health outcome, anemia, and sustained attention, a a learning outcome with some additional secondary outcomes. But for each of these, they report an adjusted risk ratio. So this was, say, the risk of anemia or sustained attention for the treatment group relative to the control group. They give a risk ratio 1.03, where 1 would be no effect, along with a confidence interval and a p-value. So the confidence interval gives you your plausible 95% interval for this risk ratio being between 0.93 and 1.13, and a p-value gives you a test against the null hypothesis that the treatment has no effect. And in fact, the results of the study was that the intermittent screening and treatment as implemented was not effective. It was consistent with sampling error, the risk ratios that they saw. So there's an example of application of hypothesis testing and confidence intervals. The basic logic of hypothesis testing is that the observation, the sample that you draw, come from one of two populations. Either a usual distribution that has been true in the past or that is associated with a control, or a potentially new distribution that is induced by your intervention or by some different condition. So one of two. And the hypothesis test will help us to make a decision as to which of these distributions we believe our sample was drawn from. And a classic example of this for one sample would be you have a handful of beans and only a few of them are white, and then you have a big bag where most are white, and because what your handful that you drew randomly from that bag is so different in its distribution from what's in the bag, you say probably those beans were taken from another bag. So that would be option 2 here. So the inference comes from a sample and saying either it's similar to what we were expecting or it's very different from what we were expecting. And whether that difference is consistent with random sampling error or not. All right, another analogy, classic analogy, is the courtroom trial. And this is used to explain how we're going to make that decision on these two so-called hypotheses, the null hypothesis and the alternative hypothesis. So in the courtroom trial, there's a defendant, and they're considered not guilty until guilt is proven. That corresponds to the null hypothesis. So in the absence of any evidence, you accept the null hypothesis. If you're needing to decide what your null hypothesis is, that is the one that you have to accept in the absence of any evidence. And then your prosecutor tries to prove the guilt of the defendant or tries to prove this alternative hypothesis. And that alternative is accepted only when there's enough evidence to reject the null hypothesis. So here's a little table to help with that. So if we have a true null hypothesis, so the defendant is truly not guilty and the defendant is acquitted, that's a right decision. Or if the alternative hypothesis of guilt is true and you reject that null hypothesis and convict, that's also a correct decision. But then there are two types of error, so-called type 1 and type 2 error. But I found here a cartoon that's a little bit easier way to remember type 1 and type 2 error. It's a pregnancy test, and with the two men, they make a type 1 error saying you're pregnant when the past condition that was true before was you're not pregnant. That's the null hypothesis. So this is a false positive or a type 1 error. The alternative with the two women here, obviously pregnant, and the doctor saying you're not pregnant, that's the false negative or the type 2 error, when in spite of the truth, the alternative hypothesis being true, the null hypothesis is not rejected. You can actually use confidence intervals for certain types of, as an equivalent to certain types of tests. Not all types of hypothesis tests, but in the instances where you have learned to calculate a confidence interval, there is an equivalent with an associated hypothesis test. So if you calculate a 95% confidence interval, when you do that, if it's the one sampled z test, you set z equals 0 where the sample mean lies, and you found values of z and then corresponding values of the measurement that contained a probability of 0.95 under this standard normal distribution. And that gave you your confidence interval at the sample mean plus or minus 1.96 times the standard error. And you could use that for your hypothesis test. All you have to do is take the value of the population mean corresponding to your null hypothesis and ask, does it fall within the 95% confidence interval? And if it does, you accept the null hypothesis. If it falls outside the 95% confidence interval, you reject the null hypothesis with an alpha or a type 1 error rate of 0.05. Because 5% of the time, even though the null hypothesis is true, you're going to reject it just because sampling error caused the confidence interval to lie outside of the true population mean. On the other hand, if you were to think of this as a hypothesis testing situation, z equals 0 would correspond not to the sample mean, but to the theoretical mean under H0. You would calculate z for your sample from the difference in the sample mean to the null population mean, calculate z, and then you would reject H0 if that value of z lied outside of the critical region, which would be anything greater than plus or minus 1.96. So without calculating a confidence interval, you could perform a hypothesis test. And I'll go through that in a lot more steps. But these both would lead you to the same conclusion. Either you reject H0, the null hypothesis, by both, or you accept for both. I'm giving you a 5-step program for hypothesis testing. And I want you to follow this through in all 5 steps, even though you're not always going to do this in the future. But I think it's useful for you to do it as you start out, to formalize the process and make sure that you know what you are doing, and to make sure that I know that you know what you are doing. This first step is really important. And it's something that you're going to be asked repeatedly to do, which is to state your null and alternative hypotheses. And I'll tell you how to do this, but I'm going to want you to do this in a formal and precise way. So having done that, you're going to specify the significance level, alpha. That is your acceptable type 1 error rate. So those are in like your planning stages. Then, this doesn't always happen in the same order, whether your sample is drawn before or your sample is drawn after. But after doing these two, you're going to calculate the test statistic. Could be using the standard normal distribution, the t-distribution. But in fact, this generalizes to a whole bunch of other test statistics, everything else that you do. But from that test statistic, you'll determine a p-value, and then compare that p-value to the significance level alpha and make your decision about whether or not to reject H0. These final 3 steps could be a little bit different if you're comparing the test statistic to a critical value. Like if you were doing a hand lookup on the table of T statistics, you might skip this 4th and not determine the p-value, but just compare your test statistic to the critical test statistic. I'll be showing this slide a few more times. All right, I'm going to talk about all of these steps in some detail now. So step 1, formulating the null and alternative hypothesis. Again, this null hypothesis states that there is no difference from the past or from what one would expect if there had been no change. And by doing that, it posits a distribution for the population from which the sample was drawn. And if it is true, then any discrepancy between your observed data and the hypothesized distribution is due only to chance, only to sampling variation. So if your null hypothesis is true, then any difference between your sample mean or proportion that you observe is only due to sampling variation. That's a hypothesis. Of course, we can't know the truth because we don't know, we don't know the population statistic for, or the population mean from the sample that we drew. We can only hypothesize this. And the alternative hypothesis states that there is a real difference. And if true, then that observed discrepancy is not due only to chance variation. There's still some chance variation, but that doesn't explain all of the discrepancy between our observed data and the hypothesized null distribution. And so, if given the data that we have, there's too large a discrepancy that it is likely to have been drawn from this null hypothesis, this is going to lead us to accept the alternative hypothesis instead, based on the data. I am going to ask you to write out your null and alternative hypotheses in a formal way, just like this. This is going to come up, and I would really like to see you just write them out in this way. So there's some key points here. This is for a 1-sample test. Sorry, this is, so sorry, this is by two-sided, I mean two-tailed here. I'm going to write this to make that clear. So this is a two-tailed test. It's two-tailed because I'm referring to the two tails of the probability distribution, of the sampling distribution. Did I change? Okay, and again, this should read, two-tail. So our null hypothesis is that the mean from which our sample was drawn is equal to the mean of this null distribution. So a couple things to point out about this First is that I'm using mu. I use mu for population parameters. So this hypothesis has to do with populations. I'm not using x or x bar or anything like that. That's a common mistake that I see in these. The null hypothesis is about the population means. And so you have to use mu to represent the population distributions. Second key point is that this is an equality. The null hypothesis is that this mean of the population that we are studying is identical to the mean of this population of the null hypothesis. And this is where it's important that you're remembering that we're talking about the population, because of course, if we drew samples from two populations or two samples from the same population, they would never be identical, because there's always a bit of sampling variation. But our null hypothesis is about the population, and if these two samples were drawn from the same population, then that population mean really is truly identical because it's the same population. I remember being kind of confused about this when I first learned about this. Like, how can this be a hypothesis that they're exactly equal? Like, nothing's ever exactly equal. Does this make sense? They're exactly equal because they're the same population. So in this example, is the blood pressure of smoking males the same as in the general population of 211 milligrams per 100 milliliters, where the null hypothesis is then that mu, the mean blood pressure for smoking males, is equal to that same 211. That's a statement of saying that smoking makes no difference to blood pressure. That's why that's an equality. Your null hypothesis is that it doesn't make a difference. And your alternative hypothesis is that these are not equal. So there is a difference. It's either greater or it's lower. It's just not the same.
So it's only, I'm sorry, so it's only the same if it's from the same population? That first part? Yeah,
so I'm saying, how can these be the same? They're the same because I should say that the thing that we are measuring is the same in these populations. So in this example, okay, smoking males are not the same population as non-smoking males, but the null hypothesis is that it has no effect on their blood pressure, so that the population mean blood pressure is the same. I wonder if it was done by me plugging in this. Let's see if that helps. Oh. Okay. So those were one-sided alternatives. They had a mu of one population equal to corresponding to our sample being equal to a hypothesized mean for the null distribution. If we are talking about a two-sample test where we have two samples instead of one, then the null hypothesis is that the means for those two populations are identical. And the alternative is that they are not identical, or that the difference between the two of them is not equal to 0. So I'm using 1 and 2 to refer to the two populations from which these samples were drawn. For example, does intermittent screening and treatment for malaria prevalence, for malaria affect prevalence of anemia in school children. So the null hypothesis in this 2-sample test would be that the prevalence of anemia in the control group is the same as the prevalence of anemia in the treatment group. So if you have an ineffective screening and treatment program, this is what you expect. If you do have an effective screening and treatment program that either helps or harms things, this is your alternative hypothesis, that these are not the same. And you'll notice here that even though we would presume that screening and treatment for malaria should, decrease the prevalence of anemia in school children, we still just use not equal. We're not using just less than or just less than here. This is the sort of standard hypothesis test is just an equality and an inequality. But it is possible to specify so-called one-sided. I actually prefer saying one-tailed here. I should have changed this just so that somehow it seems clearer to me. But one-sided, one-tailed is referring to tails of the distribution, of the sampling distribution. And an example here would be, so for a one-sample test, that the mean is less than or equal to the hypothesized mean in the null distribution. So this null hypothesis always has to contain the equality. So it can't just be less than, but it can be less than or equal to. So the hypothesis is that equality is contained in the null hypothesis, but in this one-tailed test, the alternative contains only an inequality, or only a one-sided inequality. So for example, greater than. And something similar for the means of 2 samples. And I should say that the instances in which it's permissible to do a one-tailed or one-sided hypothesis test are very rare. That there are some cases in so-called equivalence clinical trials where it's standard to do that, but most likely you'll never use this. And if you do use it in a case like with the malaria clinical trial, it's interpreted by reviewers usually as being just a way of dividing your p-value by 2 without actually being justified. So in most instances, don't use it. So yeah, it depends on the context of the problem. If you were going to use a one-sided alternative, it is something that you would have to determine in advance of doing the study. And it's not as simple as it sounds. A, because the one-sided tests generally divide your p-value by 2. And because it includes, so in the example of the cluster randomized trial, it means that your null hypothesis is not just that the treatment is ineffective, that somehow under your null hypothesis that prevalence of anemia could increase even with an ineffective treatment, which in that instance, if you think about it in terms of the null hypothesis, it would be hard to justify why you think that under a no change, like just an ineffective treatment, you could see an increase of the prevalence of anemia. It's not just because you think that screening and testing for malaria should produce a reduction in anemia. That's not sufficient justification for using a one-tailed hypothesis test. Okay, step 2. specifying the significance level alpha. This is kind of arbitrary. It's your acceptable type 1 error probability. That is the probability of concluding that the alternative hypothesis is true when it is not. So it is kind of arbitrary, but traditionally 0.05 is the most common value. And typically it's taken to be something small. And that is done under the assumption that you want to protect from this type 1 error of falsely concluding that the alternative hypothesis is true, that your data is giving you evidence of something that it is not. Yes?
So 0.01 is what?
So 0.01 would be a 1%, it would be saying that a 1% type 1 error rate is acceptable. Meaning that 1% of the time, if the null hypothesis is true, you will reject it anyways just because of sampling variation.
And 0.05 is 5%.
Yeah, 0.05 is 5%.
That's what we use with 95.
Yeah, so with an alpha of 0.05, you will either incorrectly reject if the null hypothesis is true, you will still reject it 5% of the time. And if you construct a confidence interval, you will miss the population mean 5% of the time.
And 0.01 is what, 99?
99% corresponds to the 99% confidence interval. You're welcome. So this third step, all hypothesis tests are based on calculating a test statistic. So we've only done Z and T so far. There will be other ones, but this is a key step in all null hypothesis significance testing. And what that test statistic does is it is some measure of the difference between your observed data and what was expected when the null hypothesis is true. And generally, it is something that its magnitude is small when the null hypothesis is true. And under a true null hypothesis, larger magnitudes become less and less likely. That's a general property of test statistics.
Sorry, can you repeat that, the magnitude?
So a general property of test statistics is that its magnitude, under the null hypothesis, the most probable values are small in absolute value, and become the larger absolute values become less and less likely under a true null hypothesis.
Thank you.
So for a difference in means between two samples or between a sample and a population mean, that test statistic will be either a Z statistic, or at least under the assumptions that you've done so far of normality, etc. It will be either a Z statistic when that population standard deviation is known, or the sample size is very large, so I think greater than 500 or something. Or if you estimate the standard deviation from the sample, then you should be using the T statistic, regardless of sample size. So this test statistic, you're then going to place onto a sampling distribution of that test statistic. And knowledge of that sampling distribution is going to allow you to calculate the probability of observing the test statistic that you observed, or something even more extreme. So with let's say a Z statistic of about here, then you're going to calculate the probability of something even above here. And this is only actually a one-tailed test. you typically, when you're doing a two-tailed test, will also include the mirror of this, the left-hand tail as well, to get your p-value. So this actually shows you how on a one-tailed test, your p-value is only half of what it's going to be in a two-tailed test, because the two-tailed test includes the probability under both tails. So that is step 4, calculating this p-value or probability value. And something just to keep in mind about interpretation of the p-value is that the p-value is calculated under the assumption that the null hypothesis is true. So in order to calculate a p-value, you have to assume that the null hypothesis is true. And assuming it is true, then you know what the distribution of your test statistic should be. In the cases so far, either the standard normal distribution or the t-distribution. And then you can use that distribution to calculate your p-value. And that holds for all hypothesis tests, that they involve calculating a test statistic for the sample, and then it's a test statistic for which the sampling distribution is known under the null hypothesis. And so if you assume that the null hypothesis is true, you can calculate the probability of observing your test statistic or something more extreme. So key thing from this page, I think, is that you're assuming that the null hypothesis is true when you calculate the p-value. And calculating the probability of what you've observed. Finally, step 5 is to either accept or reject the null hypothesis. If it's a very small p-value or a very large test statistic, then that provides stronger evidence against the null hypothesis, and you will reject the null, accept the alternative hypothesis. But if the p-value is something greater than alpha, so a p-value of 0.06 or 0.3, if alpha is 0.05, then you have insufficient evidence to reject the null hypothesis, and you will accept it because the sample you have drawn is consistent with that assumption of the null hypothesis being true. And then finally, you make conclusions about the question at hand based on your hypothesis test. So here are those steps again. The 5 steps, starting with stating your hypothesis, then the significance level, drawing your sample and computing the test statistic, using that to optionally determine a p-value, and then comparing that p-value to alpha or the test statistic to the critical value of the test statistic and deciding whether or not to reject the null hypothesis. And taking that and stating your conclusion in terms of the subject matter. So going back to this example of the screening and treatment test, I have some questions for you. So first of all, what is the outcome variable? I know it's kind of small text, but I told you before. There's several outcome variables. What's one of them? Anemia. Yeah, that's one of the outcome variables. So for that outcome variable, anemia, what are the null and alternative hypotheses? Put into words. Who wants to tell me the null hypothesis? No, go ahead.
So the null hypothesis would be that in both groups, the treatment and the control group, the anemia level is the same.
That's pretty close, although when you say groups, it's not clear to me that you're talking about populations, because it's not limited. The hypothesis is not about these samples. The hypothesis is about populations.
So that in both populations, school children who get intermittent screening and treatment, and those who don't, have the same proportion of
Yeah, or yeah. So I might even state like, you know, who is the population here? The population is school children in Kenya. So among school children in Kenya, the null hypothesis is that intermittent screening, this program of intermittent screening and treatment for malaria produces results in anemia prevalence that is no different than for those school children who do not receive any intermittent screening and treatment. So that makes it clear that you're talking about the population of school children in Kenya, not about these particular groups who are selected for the study. And the alternative hypothesis is that this IST does produce a difference in anemia prevalence among school children in Kenya. So the null and alternative hypotheses are about this population of school children in Kenya, not just the ones selected for this study. What's the significance level alpha? I think it's 0.05 because they state these 95% confidence intervals. What's the p-value? Let's see, for the anemia. Prevalence of anemia at 12 or 24 months. Okay, here's the one for 12 months. Adjusted risk ratio 1.03, confidence interval 0.93 to 1.13, p equals 0.621. So is H0 rejected? No, no, because this is greater than our alpha level of 0.05. And then how is this reported? Putting it into the language of the study, it says, I cut this off, the bit of conclusions here. No effective IST was observed on educational achievement, but an apparent negative effect was seen on spelling scores. Well, I'm missing a little bit here, but it was reported as being there's no effect. Yeah.
What does that do as a p-value? How do we get that?
Well, so the p-value, remember, it's based on the assumption that the null hypothesis is true. If the null hypothesis is true, then you have some test statistic that you know what its distribution is, and it's the probability of observing your test statistic or one more extreme given that true null distribution.
Get the p-value from the test statistic.
Yeah, you get the p-value from the test statistic. So here the test statistic, these are about prevalences, about risk ratios, and the test statistic for these will be, it's a good question. I'm not sure offhand which test statistic they used. It might have been a normal approximation, probably not though. But it's based on the sampling distribution for these adjusted risk ratios, which if the null hypothesis is true, that risk ratio is equal to 1, exactly 1, if you have a treatment that just doesn't do anything. So this is not too different from 1, and in fact, under the null hypothesis, you would get values of 1.03 or greater, or something like 0.97 or less, a full 62% of the time. Hurry for time. Pretty good. Okay, couple more examples. So going back to this cholesterol example, if cholesterol levels are normally distributed in US men with a mean of 211 and a standard deviation of 46, And we have this question of, do hypertensive male smokers have the same mean cholesterol level? I'm going to go through these steps. Step 1, writing down the null hypothesis. This is that will be that the mean cholesterol level for hypertensive men is the same as for that of the general population, or as a formula, H0 is that mu equals 211. So I've been careful to state this in terms of the population, not in terms of the study. The alternative is that, here I wrote group, but this is referring to hypertensive men and saying that hypertensive men have a different mean than the general population. Step 2, I'll let alpha equals 0.05. Step 3, calculate take our sample and calculate the test statistic. So we have a sample of 25 hypertensive males, and their mean cholesterol level is, well, this should say X bar. What would we conclude if X bar were 195 or if it were 227? And I'm just using here the standard deviation from the population, so I don't need the standard deviation from the sample. Taking this example of 195, I calculate Z here, get a value of minus 1.74. And then calculate the probability of a Z value less than minus 1.74. That's this left tail. And then add to that the probability of a positive Z value greater than 1.74, and that doubles the probability. So it's 0.041 or 4.1% in each tail, and we get a probability of 0.082. So this is the p-value. Yeah. And then the other value, 227, this was, so the difference here was, what is this, 16. 227 is just 16 above the population mean of 211. So the p-value is exactly the same. Because this is a two-tailed test, it doesn't matter whether the value we observe is here on the left side of the sampling distribution, the null sampling distribution, or on the right side of it. It's the same p-value. So step 5, we do not reject the null hypothesis since our p-value is greater than 0.05, and we conclude that our sample does not provide significant evidence that the population mean cholesterol level for hypertensive males is different from the overall population. So does this mean that we're 95% confident that they're the same, that H0 is true? No. That's an important distinction. We're not providing evidence for the null hypothesis. All we're doing is we're saying that we don't have sufficient evidence against it. We're saying that we can't be 95% confident that H0 is false. We set out saying that we want, we only want to reject the null hypothesis if we can be 95% confident that it is false. But then if we fail to reject it, that does not give us a similar confidence in the truth of H0. And as a simple way to maybe example to give here, if you use a very small sample, like say we had only measured 5 individuals here instead of 25, it would be even more difficult to observe any difference because our standard error would be quite a bit larger. And we have less data on which to be able to reject the null hypothesis. We probably still would not reject it, but this 1 minus alpha is still 95%. So this doesn't change depending on the size of our sample. Alpha is just something that we determined in advance. All right, I have an example of a one-sided z-test here, just to demonstrate if you had a null hypothesis of mu greater than or equal to 211, and an alternative of the mean of hypertensive smoking males being less, then in this instance, it does matter whether your observation is 195 or 227 or whatever that was. But because it is negative, our probability under the left step is 0.041. So in this case, we would have rejected the null hypothesis. So this is only to show that under the two-tailed test, sometimes it really matters which one you choose, and it had better be well justified if you're not using the two-sided test. On the other example, if if we had done the other one-sided test, then we would have ended up with a p-value of 0.959 if it was the mean being the null hypothesis including lower values instead of the null hypothesis including higher values. So this calculation becomes a little trickier for the one-tailed tests. So the one-sided p-value is half the two-sided p-value if that sample mean is consistent with the direction of the alternative hypothesis. If it's in the other direction, then you end up with a very large p-value. And these one-sided tests have to be carefully justified because they're usually, most journals expect you to use two-sided tests in almost all instances. For proportions, just like with confidence intervals, you can go ahead, as long as it is a large sample, you can use this, this normal approximation for the binomial distribution with the mean and the standard error as we calculated before. So just summarizing, the hypothesis tests and confidence intervals provide alternative ways to decide whether or not to accept the null hypothesis. If the confidence interval contains, if the hypothesis test is about a single sample and a population mean, then all you have to do is look at whether your confidence interval contains your null mean. If it does, then you accept the null hypothesis. If it does not, then you reject the null hypothesis. So you can do that for one sample hypothesis test, but not for two sample tests. This is a misconception sometimes that for two sample tests, you just calculate like a 95% confidence interval for each of them and look at whether those two confidence intervals overlap. That's incorrect. You can have cases where the difference in the two means would lead you to reject the null hypothesis, but those confidence intervals still overlap. We're going to get to two sample hypothesis tests next week. But in short, if you were to use a confidence interval in place of a two-sample hypothesis test, what you need is a confidence interval on the difference in those two means. right? So a confidence interval on the difference in means, not confidence intervals for each of the means separately. We're going to get into power more next week, but I want to introduce it here just to say, so we've learned about type 1 and type 2 error and the instances where there is no error, but there are two cases of, and there are two cases where you can be correct when the null hypothesis is true and the null hypothesis is false. But this type 2 error, 1 minus that is what we call the power. So the power is if you have a false null hypothesis, it is the probability that you correctly reject the null hypothesis. So far we've had type 1 error alpha, type 2 error beta. Alpha was the male doctor, male patient saying he's pregnant. Beta was the female patient saying she's not pregnant. The power is this instance where the null hypothesis is false, so the patient is pregnant and correctly saying that the patient is pregnant, for example. So just some basic ideas is that this type 2 error goes down and the power goes up if your as your alternative hypothesis value gets further from the null hypothesis. That is, if the true difference in means gets larger, they become easier to see. Your power increases. Power is a nice word because it sort of fits into statements about like the power to observe a true difference. Conversely, this type 2 error decreases and the power increases as the variability decreases. So if there's very little natural variability within the populations, it becomes easier to see the same difference in the populations, or as your sample size increases, because as sample size increases, your sampling variability in the mean decreases. The type 1 error stays the same no matter what mu1 is. We just fix the type 1 error. So whereas it's the type 2 error that changes for a fixed alpha. In general, we want high power, and this is something that comes in when you're planning a study based on pilot data or some previously published study. And when you're planning a study, you would like high power. So you don't want to do the study if you don't think that you're going to have, say, 80 or 90% chance of detecting a true difference based on your intervention or your difference from the previously known population value. So in summary, alpha is what protects your readers from spurious results, whereas power is what protects you from negative studies when important differences are actually present. And we will return to how to calculate power. So finally, just some take-home messages here. If we fail to reject H0, is the probability that H0 is true equal to 1 minus alpha? I couldn't even stand to leave it up there without giving a hint. No. It's a very common misinterpretation of type 1 error rate and the p-value. So that is to say that failing to reject H0 is not evidence to say that H0 is true. It just means that you have not been able to observe evidence against it. Could be because you had an underpowered study. It could be because the true difference is very, very small. you can't actually say that like a difference in means in the population is exactly 0. You can just say that it was not large enough for you to observe a difference in your study. Failing to reject the null hypothesis, even though the null hypothesis is false, then the alternative is true. That's type 2 error or beta, and 1 minus that is the power of the test. And just to make a note, statistical significance is not necessarily the same thing as practical significance. And this can be important when you get to very large sample sizes. When you have a very large sample size, your point estimates in the mean or whatever else become very precise. So a very small difference could become statistically significant, but at that point, potentially it might not be practically significant. So if you had observations on 1 million blood cholesterol levels, you could determine a very small difference in means, but that might not be clinically significant, that small difference. All right, so let's take 5 minutes and then let Tony take over. Any questions? This is going to be tricky shutting this off without the use of a keyboard.
I don't understand why I did this.
What's up?
That was working before.
Yeah.
Is it plugged in?
Yeah, I know. I even used it when I signed in. So I don't know why it's not working anymore. Oh, wait, that worked.